Welcome to Magnetism and Electromagnetism Lesson 6. This is a physics only lesson and we're going to be looking at electromagnetic induction, which will include generators and dynamos. My name's Mr. Pratt, Director of Science. And for the lesson you're going to need pen, paper and exercise book to record some notes and to do a few questions in. Get your mobile phone out of the way unless you're needing to view this video on it. Avoid all the distractions that you can. The starter then. I'm going to give you 2 minutes. I want you to explain how 3 factors affect the size of the force produced on a current carrying wire magnetic field. So we're talking about the motor effect from the lesson before. Halfway through your time, you might have listed the factors, but make sure you explain them as well as listing them. Let's list them first and then we'll talk about how we turn that into explanation. So your 3 factors are the magnetic flux density, so the field strength, and that's the letter B in the formula. The amount of current in the conductor, I, measure that in amps, and the length of the conductor, L, in the magnetic field, and that would be in meters. So we've got our 3 factors. When you need to explain them, let's do the first one, and then you should be able to understand what you're doing with the others. So I would say if the magnetic flux density is increased, the force would be increased. And for the second one, if the current is increased, the size of the force is increased. And number 3, if the length of the conductor is increased, then the size of the force is increased. Because the equation is F, the force, equals B times I times L, each one of those is directly proportional. So the force is directly proportional to the magnetic flux density. So if you double the magnetic flux density, you would double the force, and the same is true for the other 2. Our outcomes then. First, we need to describe what the generator effect is. We had the motor effect last lesson, and this is linked to it. It's essentially the same physics for both. And also then to apply the principles of the generator effect to an AC generator and a DC dynamo. We've got a couple of other applications as well towards the end of the lesson. Before I start explaining to you about the generator effect, what we've got there is linked to it, and because you will have come across this in the energy topic, generating electrical energy is linked to energy resources in the energy topic. So if you've got a wind turbine diagram there, it's attached to a generator inside, and from there we can produce electrical energy. I'm going to give you 2 minutes. I want you to try and describe how it happens and what you think is inside that generator. It could be that you can't remember at all, but you might have some idea. Halfway through your time. If I talk through that diagram, starting with the rotor blades, it won't do us any harm to understand how this thing is working in general, not just the generator bit. So the wind energy, that's kinetic. So you've got kinetic energy store in the wind, and that kinetic energy store from the wind causes the rotor blades to spin. So you then end up with a kinetic energy store in the blades as they rotate. The blades are connected to a drive shaft and a gearbox. All the drive shaft does is just carry that kinetic energy store through the gearbox and then to the generator. The gearbox allows you to control the speed that the generator is turning. We'll mention more about that when we look at the generator in more detail. So going back to the questions, question 1, how does it happen? Well, you might have tried to answer by talking about energy stores. So if you've said that the kinetic energy store is transferred into the generator, which produces electrical energy transfer, yeah, you're along the right lines. But what's inside the generator? A generator is made up of magnets and coils of wire. All that happens then is that the magnets are rotated within the coils of wire, and that's how we generate electricity. The rotating bearing underneath that diagram there is so that the whole thing can turn into the wind to get the greatest amount of kinetic energy out of the wind possible. In the previous video, we looked at the motor effect. So with the motor effect, we can get movement on a wire, and that's the same wire that we used before. We can get movement on the wire by putting an electric current through it when it's in a magnetic field. So it's the same bit of equipment, but before we had an ammeter in there, we connected it to a power supply, we had a current running through it, and we get movement. If we reverse the current, the movement would be reversed. If we reverse the magnetic field, the movement would be reversed. You've got the idea. So now we're looking at electromagnetic induction. So it's not a force and a movement that we're making this time. This time we're going to induce a voltage in this wire. So let's get used to the word voltage.
potential difference measured in volts. Let's get used to the word induced. The word induced means forced or made. If a birth is induced, it's been pushed into happening. You've waited long enough, let's induce the birth. But we've still got the same factors in play here. We've still got a magnetic field, but this time I'm going to put the movement in, and the movement is going to generate a potential difference. So the multimeter here now is measuring millivolts. We are looking at a very small amount of voltage at the moment that we're going to induce. Multimeter's reading 0, so that's 0 milliamps. And I'm just going to move the wire, and I'll move it up to start with. Okay, nothing, let's do it again. Okay, got a little bit, yeah, 0.2 of a milliamp. Let's do it again, let's move it up. 0.1 of a milliamp, move it up again. 0.1 of a milliamp. A tiny amount of voltage. Let's just tighten it up and then move it the other way. If I move it down, making about the same. You will notice that if I move it up, the negative sign flashes. If I move it up, negative sign flashes. If I move it down, no negative sign. I'm getting a different voltage by going up and by going down. When I go up, nothing. When I'm going up, I get a negative voltage, and down I go the opposite way. So the direction that we have this movement all determine the direction of the voltage, and if this was connected to a bulb, we'd get a current flowing as well. So the induced voltage, V equals IR, will push a current around the circuit. That's a really small effect, so let's step it up and let's just try and see it slightly more convincingly. I'm going to get not a single wire now, but a big coil. This coil's only got 5 turns on it. We'll connect that to the multimeter. Again, we're measuring the potential difference. Different magnet this time, just got a bar magnet, permanent bar magnet. 0.3 when I push the thing in. Let's do it again. 0.3. Watch what happens when I pull it out. Nothing. Watch what happens when I pull it out. We've got a minus 0.6 of a milliamp. So when I put it in, I've got plus 0.4 of a milliamp. When I pull it out, minus 0.4. So the direction that I move it in is affecting the direction of the potential difference. So instead of me pushing the north pole in this time, remember going in like that, that was positive. Flip that around, push the south pole in. I get negative when I go in, so negative when I go in, negative when I go in to go a bit further, and positive when I come out. So I can reverse the direction of the potential difference by reversing the direction of the movement or reversing the direction of the magnetic field. So that was a slightly bigger effect than before. Let's step it up. So let's not use 5 turns. Let's have a look at this one. If I connect across there, I've got 2 coils of 1,200 turns each. So that gives me 2,400. So 2,400 turns. Right, getting a bigger effect, I'm going to have to turn the voltmeter up. So I'm now dealing with volts instead of millivolts. So I'm getting, well, I've got 0.1 of a volt there, 0.2 of a volt. Let's move it really slow, see what happens. And fast out. Faster in. The speed's having an effect as well. Let's just get some idea of what we're making. 0. Well, I've got 0.2 there. Let's step that up now. To this coil, if I connect there and there, I've got 5,000 turns, so I've got more turns. 3.5 that time, so I'm generating a greater potential difference. I'm inducing a greater potential difference. Put the south pole in. Should get it going the opposite way around.
Electromagnetic induction then. So this is the term that we use to describe electricity being created in a wire. You need to be a little bit careful that you don't confuse potential difference in current. Now in that last video clip, I had this habit of using milliamps instead of millivolts. It was a voltmeter that I was using there on the multimeter. So if I've got a reading of volts, that reading of volts is the potential difference. If you have a potential difference across something that's a conductor, like a circuit with a bulb in it, then you'll get a current flowing. So potential difference equals current times resistance. Just going back to the electricity topic, V equals IR. By moving the magnet in the coil of wire or even next to the coil of wire, if you've got a circuit, then a current can be induced. That word induce means force. We're forcing it by moving the magnet. You only get a current induced and a potential difference induced if the magnet or the coil or both is moving. If you keep it still, you'll have no induced voltage or current. There's two ways that you can generate the current. You can either move the wire, so it moves, it cuts through the magnetic field. Think of that magnetic field as the lines, and then you've got your wire cutting through those lines in the magnetic field. You could do that. Or you could move the magnet in and out of the coil, in which case it's the magnet that's moving, but you've got the same effect. You've got those magnetic field lines being cut by the current carrying, by the conductor. You cover more if you go on to study A-level physics here. When you get an induced current, that current will make a magnetic field that goes against the original magnetic field. In other words, when you push a magnet through a coil of wire, the coil of wire will produce a magnetic field, but the two magnetic fields will push against each other. Can you think what would happen if that wasn't the case? Well, you'd start moving your magnet in a coil of wire, and then because the magnetic field was pulling it, it would sort of go on its own, and that would allow you to generate electricity without putting any effort in, which would, from a physics point of view, be impossible. If you want to have a further look at this, if you go on a website and look up Lenz's law, L-E-N-Z', it'll describe more on how it's always in the opposite direction. So how can the amount of current be increased? Pretty much common sense. You could increase the number of coils because that's giving you a greater length of wire. You could increase the speed, so you're cutting these field lines faster. Or you could increase the strength of the magnet. Increasing the strength of the magnet would put the field lines closer together, which would mean you were actually cutting those field lines more often.
We're going to look now at modelling the way that electricity is generated. You should recognise this as just being exactly the same DC motor that we had in the last lesson looking at motors. Coil of wire between two permanent magnets. We've got, if you remember what that's called, commutator. Every half term, the commutator swaps the connections around on that side. If I just move you a little bit closer, you can see those connections just on that side swap every half term. There's a bit of wire just touching the other bit of wire. I've connected this to the multimeter, still on volts, and it's on millivolts. I'm not expecting to be able to generate much voltage. I'm going to spin it. So I'm spinning it this time, spin it with a pencil to start with, and as I spin it, you'll notice we're generating a voltage, inducing a voltage. If you imagine now that this spindle was connected to a wind turbine, and the wind turbine, let's make sure my connections are touching, the wind turbine is rotating, you can see as it's rotating, touchy connections, as it's rotating, it's generating a potential difference there. Not much, but a potential difference. Because the connections are swapping every half turn, even though this is rotating, we end up with a direct voltage, which will give you a direct current. So what we're looking at now is a DC dynamo. So because the connections are reversed, this, as it's spun round, will generate a direct current that will flow to the circuit. This would be quite useful for charging a battery, say. Sometimes you'll have a rechargeable battery and you've got a handle and you can turn it. I've got a little radio like that, and as you rotate it, you're generating electricity and charging the battery up. So this is a dynamo. Now the only difference between a DC dynamo and an AC generator, in an AC generator, you're rotating it and you're not swapping the connections around. In a generator, you're going to make AC. And when we're using a generator on the national grid, like in a wind turbine, or in a coal powered station where you're heating up water to make steam that drives a turbine that drives the generator, that will make AC. If you remember back to the AC topic in electricity, the AC voltage is about 230 volts and it's 50 hertz. That means that you get 50 rotations a second. So when we're turning a generator in a power station, we're rotating it 50 turns in a second, which will give us a 50 hertz AC generated.
This diagram shows how you could use a normal fuel, it could be gas, it could be coal, in a boiler. You produce steam and then you're generating electricity. So it's a model of us generating electricity that goes in the national grid and then serves your homes and factories. So on the left we've got the boiler. So we're turning cold water into hot water into steam. You get steam coming out at the top under pressure. That will then cause the turbine to rotate. So we've got our kinetic energy store. That then causes magnets to rotate inside the coils. That will induce a voltage across the coil. And if that's then in a circuit, you'll have an induced current that we could then use, like in that diagram, to light up a light bulb. What's not included in there is the transformers that we need on the national grid. That'll be the final lesson on the electricity, on the electromagnetism and magnetism topic. What I want you to do now, 2 minutes, is we've got 4 sentences which will serve as notes for you. Some of the sentences are true, in which case, if they're true, just copy them out. If you think they're false, you'll need to make a little amendment to make them correct and then copy them down. 2 minutes. first sentence then was true, so you should have just copied that down, and sentence number 4 was also true. Sentence number 2, we need to change the stationary to moving. Electricity can only be generated when a magnet is moving within a coil of wire, or the coil of wire is moving around the magnet. Either one is true. Number 3, the amount of electricity induced is increased by increasing the speed at which the magnet or coil moves. A 6-mark question then. The biggest problem you might have is getting all of the marks, because it seems like a very straightforward question, but when you see it's worth 6 marks, you should be breaking it down into as many steps as possible. A little hint: talk about induced voltage and then talk about induced current, because it's an ammeter, so we're talking about current here. I'm going to give you 4 minutes, so 2 lots of 2. You're almost halfway through your time. We're just about finished. let's make sure then that we're only writing down what we need to write down. So we've got an ammeter with the 0 scale, centre scale. So you can see at the moment it's pointing straight up and we've got a 0. So when a current flows, it's going to move left or it's going to move right. The teacher moves the magnet slowly towards the coil. So we don't have to describe what's going on and explain then what's going on when it comes back out. We're just talking about moving towards it. Let's try and break it down in steps. See what you've got, and then I'll give you 30 seconds or so to look at the mark scheme just to double check how many marks that you've picked up. So we'll start with the magnet. The magnet is moving towards the coil. I would start off by saying that the magnetic field lines, or the lines of flux, cut through the coil. So imagine the magnetic field, drawing it around that magnet as we've drawn it before. And as you move the magnet towards the coil, the magnetic field lines cut through the coil. As the magnet is moving then, we will have an induced potential difference first. So we've got an induced potential difference across the coil. Because we've got a circuit flowing, complete circuit there from either end of the coil through the ammeter, because we've got a potential difference, an induced potential difference, we will also have an induced current. So a current will flow through that ammeter and cause a reading. The faster we move the magnet, the more of a current reading we'd expect. If you understand how an ammeter like that works, it uses the same principle. It's got a tiny coil on it attached to the needle, so as the coil is effectively moved by the current that's flowing through it in the magnetic field. So it works in the same way. What I'll give you then is the mark scheme, and you can work out how many of them you've picked up. So talking about magnetic field around the magnet's 1. Magnetic field changing or cuts through the coil is worth a mark. Induced potential difference, complete circuit, and a current is induced for your 6 marks. If you've picked up 4 or more, that's fantastic. A further 2 minutes then, part B of the question. We've got a table there and it explains on the left hand side what actions are taken by the teacher. You've just got to say what happens to the ammeter reading. It's the same as the question above, so we're going to get the needle moving left or right depending which way that the current is flowing, and this is worth 4 marks. There's 20 seconds left. second statement down is the easiest. If you've got your magnet stationary within the coil, you've got no movement, so you'll get nothing, no reading on the ammeter. Top one then holds the magnet stationary and moves the coil slowly towards the magnet, so we get a small current flow in there, so your ammeter would show a small reading. Third one down moves the magnet quickly towards the coil. It'll move, but it'll be a greater reading. Then if you reverse the magnet and move it slowly towards the coil, you'll get the same as you started with, but it will be in the opposite direction. Hopefully now then you can describe what the generator effect is. So we need to apply the generator effect, and first of all we're going to apply it to an AC generator. Another word for an AC generator is an alternator. Now luckily the word alternator begins with an A, so if you can remember, alternator is AC, and then in a couple of minutes we'll look at a dynamo which is generating DC. The structure of both of them is pretty much the same. We've got a coil of wire, there's a handle on this one so we can rotate it. It could be connected to a wind turbine or anything else, and we rotate it within a magnetic field, and then as we rotate it we get an induced potential difference, and then a current can flow if it's connected to a circuit. So in steps then, step by step, the coil's rotated, so it could be with a handle or whatever it's connected to. The conductor, that's the coil, cuts through the magnetic field. Then we get a potential difference that's induced, and the potential difference is alternating. The connections aren't swapped over each turn, so we've not got a commutator on here, we've just got two rings, if you look, that's connected to the coil. So we generate AC, and the graph there shows what AC electricity looks like. We've got the potential difference in volts up the side, and we've got time on the bottom. So we get essentially a sine wave, and that wave, one full wave there, corresponds to one full rotation. So if you look at the time on that graph for one full rotation, one wave, that is 20 milliseconds. So 20 milliseconds is 20 divided by 1,000 seconds. That's the time period. If you think back to the waves topic, the frequency is 1 divided by the time. 1 divided by a 20,000th of a second will give you 50 hertz. So that would be rotating at 50 times per second, 50 hertz. The national grid produces our AC at 50 hertz in the UK and pretty much most of the world. The two rings that you see there, they simply stop the wires from tangling. They're not reversing the connections. They just allow the whole thing to rotate without you getting a big tangled mess. So that's the alternator, and the alternator produces alternating current. Dynamo then. Dynamo begins with the letter D. D for DC. It looks pretty much the same. Coil is rotated. Conductor cuts through the magnetic field, so that's the same as the alternator. We get a potential difference that's induced. The potential difference is always in one direction though now, because on this one we've got a commutator. So the connections swap every half turn. So we end up with a voltage that's always in the same direction. So this would give us a direct current if it was in a circuit. So the current will always be flowing one way around. The graph of DC looks like the one that you've got there. Straight line, it's just staying at one particular voltage. It's not going up or down as time goes on. As the potential difference is induced, it's always in one direction. Any current that you get will be DC, direct current, so it'll just flow in one direction around the circuit. Let's move on to an application then of electromagnetic induction, and this is the microphone. Principles are exactly the same thing is going on. We've got the bits that you need to know is we've got a coil that can move, and that coil is inside a magnet. So when sound waves reach the diaphragm, they cause it to vibrate. Just like if you've got your music on loud enough, your windows are vibrating. So that vibration then, it causes the diaphragm to vibrate, which is attached to a small coil. So the coil vibrates. So the coil is vibrating inside a strong magnetic field. So we've got movement of a coil of wire inside a magnetic field. So we get an induced potential difference across the ends of the coil. So the microphone then, if that's connected to a circuit, a current will flow out of the moving coil, and we can use that current. That current will be an alternating current, and the vibrations of the current will be the same as the sound waves that have come in. So if we amplify it, we can either record it, or if you amplify it and put it to a loudspeaker, then that would work as a sound system on a stage for somebody singing. Now the speaker next, this is an application of the motor effect. So not of the generator effect, but the motor effect. So here we're looking at movement, but the principle's exactly the same. Got a magnet, coil of wire, and this time we've got a cone. Almost identical apart from its size to the loudspeaker. So you put an alternating current through that coil, and because that coil is in a magnetic field, you'll get an alternating magnetic field. And that magnetic field will cause it to be attracted or repelled from that permanent magnet that's next to it. So the cone will vibrate, so it moves backwards and forwards. And as the cone vibrates, it causes compressions, that squashes, and decompressions, that stretches in the air. And that's what a sound wave is. There's quite a lot of other physics in this that links to stuff that you've previously done. Let's see if you've got that. I'm going to give you 4 minutes on this question about a moving coil loudspeaker, so the loudspeaker. I'm not going to read it out. I'm going to tell you it's worth 6 marks, and I'm going to give you 4 minutes to do it in. You've had a minute then. If you are struggling, just rewind the video a little bit and just have a look at the points I put down about 2 minutes ago. Just about a minute left. You need to break it down into enough steps here in your explanation because it's worth 6 marks. If you can be picking up half marks on your higher paper for triple physics, you should be comfortably on for a grade 6. So have some idea in your head about where you need to be on these long questions. I've broken the answer into 6 steps. These 6 steps are quite important because in the final lesson on transformers, it's a very similar way that we're going to explain the function of a transformer. So number 1, alternating current moves through the leads. So I've started on the flexible leads there. Alternating current moves through the leads to the coil. Alternating current induces an alternating magnetic field. Alternating magnetic field cuts through the magnetic field around the permanent magnet. So then we get a force between the coil and the magnet, and that causes the coil to vibrate. The paper cone vibrates because it's attached to the coil. And the vibrating cone compresses and decompresses the air, causing a sound wave. Summary then. We've got a diagram of the alternator, AC. We've got a diagram of the dynamo, DC. Loudspeaker, microphone, and how we would increase the amount of current or potential voltage that we induce. So I'll see you next time for the last lesson on the magnetism and electromagnetism topic.